Welcome to the video for Lecture 18, Section 1. This video is about block diagrams for multi-loop control systems and how to simplify them. When we are done with Lecture 18, we will have covered block diagrams for feedback control with either cascade control or feed-forward control. This builds on the block diagram algebra and reduction material in Section 12 of the course packet. Near the end of the Section 12, we had an equation for a single loop process control system that could describe both servo and regulator problems. Servo problems were when the set point was changed. Regulator problems were when one of the uncontrolled inputs changed. Here is such a single loop process control system and the corresponding equation for both a servo problem when R changes and a regulator problem when N changes. This diagram and equation is different from ones you have seen before because this is a transfer function. There is a transfer function G4 attached to the changing input N. Single loop process control is fine, but many practical control systems have multiple loops. Two control systems with multiple loops describe feedback plus cascade control and feedback plus feed-forward control. The sketch shows a two-loop system, which is an example of cascade control. There is an inner loop that contains GC1, G1, and H1. The outer loop contains the inner loop plus G2, GC2, and H2. The reason for adding multi-loop control is to make the process or system handle multiple load changes more efficiently. Adding cascade and feed-forward increases the process response speed, especially for slow processes and processes with lag. You can have a slow process if the time constant is very large, say in the range of minutes or hours. With such a slow process, it would take the controller a long time to respond to a change in the input. A process lag is developed if you have multiple first-order processes in series. Say you had 5 tanks in series, and something happens to the flow into the first tank. There will be a delay before the 5th tank would see a change. By adding either cascade or feed-forward control, the overall system response will speed up. For this video, we will focus on adding cascade control. Please remember that when I say cascade control, we really mean feedback plus cascade control. So the block diagram with cascade control will have two loops: the regular primary feedback control loop plus an inner or secondary loop. The inner loop responds faster than the outer loop. The inner loop usually uses proportional control alone with a fairly large Kp value. For this video, we will focus on adding cascade control. Please remember that when we say cascade control, we really mean feedback plus cascade control. So the block diagram with cascade control will have two loops: the regular primary feedback control loop plus an inner or secondary loop. The inner loop responds faster than the outer loop. The inner loop usually uses proportional control alone with a fairly large Kp value. The Kp value produces a quick response to changing errors. The outer, slower loop usually uses Pi or PID control. Both loops need to be stable, and we will talk about how to assess whether a loop or process is stable later. Cascade control can be used when there's some internal process information that can be used to make a process adjustment. Using the internal process information to make an adjustment means that changes can be made sooner than waiting for the process output to change and indicate an adjustment. By combining feedback control with cascade control, the overall process response can be more stable and faster responding than a conventional single-loop feedback control system. Here is a cascade control system. There is an outer primary loop and a secondary inner loop. Both loops have sensors with feedback elements. The inner loop feedback element is H1. The outer primary loop feedback element is H2. Both loops are using negative feedback comparators. The controllers are labeled GC1 and GC2. The process output is C and the process set point is R. Our ultimate goal is to find the overall transfer function for the two loop systems C over R. The first step will be to reduce or eliminate the inner loop. So we want to find the transfer function y over x. Y is the output function for the inner loop, and x is the input function for the inner loop. If we write the transfer functions, starting at the output, we can write that y, the output function, equals E1 times GC1 times G1. Then we can write that E1 equals x minus y times H1. Combining the equations to eliminate E1 and reorganizing produces the transfer function y over x, which is GC1 times G1 over 1 plus GC1 times G1 times H1. Now that we know the transfer function y over x, we can replace the inner loop with the transfer function we found to produce the single loop control system shown here. Now we can find the overall transfer function C over R. Again, we write the transfer functions starting at the output C. The second equation is for the error term. Then we go through some algebra to separate out R. When we are done, we get this overall transfer function for C over R. We can simplify this expression by multiplying the numerator and denominator by 1 plus GC1 times G1 times H1. This slide shows the simpler transfer function C over R for the feedback plus cascade control system we had. We can replace the entire block diagram with a simple block, with R as the input and C as the output, and the transfer function we just found in the block. This slide compares the initial block diagram and the overall transfer function for the feedback plus cascade control system. This brings us to the end of the Lecture 18 Section 1 video. Write down any questions you have and bring them up in class or lab.